inner product spaces and Hilbert spaces. So two topics we're going to see. So what is an inner product space? So V is given to be a vector space over a field F. F is either R or C. There exists a map if there exists a map from V cross there to F such that psi is linear in first variable first condition. Second condition, psi is conjugate symmetric. The third condition is psi of x comma x is norm of x square for all x belonging to V. So if psi satisfies this thing on V, then we say that V is in a product space. So V is a map on V cross V. So the product V with V, this is the Cartesian product. Cartesian product. And then there is the word is the inner product and the space is there. So on the Cartesian product we have a map and that map is linear conjugate symmetric. So what do we mean that? We mean that psi is linear in the first variable, so the psi is sometimes denoted by this also. Usually it is denoted by this thing. So this is in fact a map from V cross V to F. Psi is linear in the first variable means x plus y comma z is x comma z plus y comma z. This is there. And psi of alpha x comma z, alpha, this is the linearity property where x, y, z belong to V and alpha belongs to F. This is for all. The linearity. The second condition is conjugate symmetric. So inner product of x with y is nothing but inner product of y with x bar. The second condition. And the third condition is x with x is norm of x square for all x and y belong to V. So this is the first condition, this is the second, this is the third condition. Okay. If this is satisfied, then we say that such a space is an inner product space. So this, or rather this is an inner product on this thing. An example of the inner product you have seen is Rn. And the inner product map is defined this way. So if x and y belonging to V, so x is a tuple and y is this tuple, and x dot y is x1 y1 plus x2 y2 plus xn yn. This is there. This is in fact in a product space, so it's a linear in the first variable. It's easy to see that. And how is that? You can easily check it. So maybe say if we have maybe say x is this one, x dash is maybe x1 dash comma x2 dash xn dash, where each of this xi belongs to f, each of this yi belongs to f, and our f is the real, maybe in this case then x plus x dash comma y, this inner product would be nothing but x1 plus x1 dash plus so on multiplied by this, multiplied by here with y1, xn plus xn dash yn. So this is nothing but x1 y1 xn yn plus x1 dash y1 xn dash yn. So this is nothing but the inner product of x with y plus inner product with x dash with y. Similarly, alpha is easy to check that. So if alpha is any scalar, so it's just a real number, so it would be component wise multiplication to each term so that alpha comes outside. And it is a conjugate symmetric, as we don't have to check for conjugacy, it's a real space. Inner product of x with y with x, and inner product with x would be nothing but x1 multiplied by x1. This is x1 square, xn square, so this is nothing but the 2 norm of x. The Cauchy-Schwarz inequality. So if you have x and y, inner product of x comma y, this is always less than equal to norm of x times norm of y. So the absolute value of the inner product, so if you have a V, which is an inner product space, then on V, norm is generated via the inner product. So if you take any two elements, x and y, in the inner product space, and you take the product and take this absolute value. So if it is a real vector space, so what you do is that the absolute value is there. If it is a complex vector space, then it is modulus. Okay. And the norm of x and norm of y would be nothing but the square of the norm is the inner product. So in that case, it would be the absolute value inner product with x and the absolute value inner product of y with y. So this is what we are trying to prove. So the inner product, so V is given to be an inner product space over the field F. Okay. Then this is true for all x and y belonging to V. Okay. The point is that if we take if case y is equal to 0, then what one can see easily is that inner product of x with 0 is what? This is inner product of x with 0 plus 0. So this is inner product of x with 0 plus 0, and then it would be the conjugate of this thing 0 plus 0 property. Rather 0 plus 0 would come here as a conjugate symmetric is there, 0 plus 0 comma x. Now the bar of this thing is that this is 0 comma x, linearity in the first variable 0 comma x. This is nothing but z1 plus z2 bar is z1 bar plus z2 bar, 0 comma x bar plus 0 comma x its bar, and this would become what? Nothing but x comma 0 plus in a product with x comma 0, which is nothing but 2 times x with 0. This is what? X with 0. So what do we have? From here we get that clearly shows that x comma 0, this should be the 0 of the field. So the inner product of every element with 0 may be in the second place. Even if 0 is in the first place, it is still 0. But if y is 0, then the inner product is 0. And clearly norm of 0 is 0, and norm of x into 0 as a real number product is 0. So we consider the case only the case when y is non-zero. So in that case, what would happen? So we have an element y, we can divide by a norm of y. It's a well-defined object. And if you call this object as y dash, norm of y dash, as one can easily see, is 1. So what happens is that even in the inner product space, so what we are trying to prove is that this value is less than equal to norm x times norm y. And when you divide by norm y, this is what inner product of 1 by norm y, inner product with x with y, absolute value, norm of x, and so on. What would happen is that norm is a non-negative object. If it is a non-negative object, then this is this goes 1 upon norm y, inner product of x with y, and then less than equal to this thing, norm of x. And this is non-negative term, and it's just a real number, so there is no problem in bringing this in the second place. In the first place it would be as it is. If we try to bring this in the second place, we have to take the bar of this thing, but since it is a real number, the bar, there is no imaginary part. We can write this thing as inner product of x with y upon norm of y, less than equal to norm x. This is what we want to prove. But the point is that if this object is nothing but your y dash, so we are trying to prove the thing is that so all, if suppose y dash is a norm 1 element, so what we want to prove is that inner product of x with y dash, norm of this thing is less than equal to norm of x. This is true, but we want to show all x belonging to V. Okay. The parallelogram law. So if we have two sides here, and if we complete the parallelogram over here, and suppose this is a vector x, this is a vector y, this is again y, this is x, and this vector over here is x plus y. And this vector over here is x minus y. So what do we have? We have that the sum of the squares of the diagonal from Euclidean geometry is sum of squares of all sides, that is norm of x whole square plus norm of y whole square plus norm of x whole square plus norm of y whole square is in fact norm of x plus y whole square plus norm of x minus y whole square, which is nothing but this square plus this square is norm of 2 norm of x square, and this is what 2 norm of y square. This is 2 times norm of x whole square plus 2 times norm of y whole square, norm of x plus y whole square plus norm of x minus y whole square. So this is elementary property from the Euclidean geometry. So we'll try to show that because the norm and the inner product are related, in fact this is also the true. So if V is an inner product space, and let's take any two vectors. So V is any inner product space, then for any x and y belonging to V, the following is always true. 2 times norm of y whole square. So LHS, this is our LHS and RHS. Norm of x plus y whole square, this is nothing but the inner product of x plus y with x plus y. Norm of x minus y whole square is inner product with x minus y, x minus y. So let's open it up. So what is this one? So LHS. Inner product of x plus y with x plus y, this is equal to x inner product with x plus y plus inner product of y with x plus y. This is equal to inner product with x with x, x with y, inner product with y with x plus inner product with y with y. And inner product of x minus y with x minus y, this is inner product of x with x minus y plus inner product with minus y, x minus y. This is inner product of x with x plus so this is a minus, and because here a scalar comes conjugate, because it is just a real scalar, so minus inner product with x with y, whereas here minus inner product with y with x, and then it is minus here, minus comes outside with no conjugate because just real, so its conjugate is just real, so minus becomes plus inner product with y with y. So this is nothing but inner product of x with x minus inner product with x with y minus inner product with y with x plus inner product with y with y. So if you add over this term, look at this object over here is a positive sign, and this object over here which is negative sign, this object with a negative sign, this object is a positive sign. This cancels out, this cancels out, this and this is there. So this addition with this addition is nothing but 2 times inner product with x plus 2 times inner product with y, which is nothing but 2 norm of x whole square, norm of y whole square. What is this object? Norm of x minus y whole square. This object is nothing but norm of x plus y whole square. So this square plus 2 times this square plus 2 times this square is norm of this plus norm of this thing, square of this thing. So this is the parallelogram law. So let's write it down. For all x and y, where V is what? Inner product space. Inner product space and the inner product map. So psi, which is a map from V cross V to F, where V is the inner product space, over the field F. Psi is continuous map. So, in the sense that, so if you have, so you can fix the one variable and so on. So psi is nothing but denoted by this comma this also. If you have a sequence xn and another sequence yn in V such that xn converges to x, yn converges to y in the norm, which is arising via the inner product of x with x is norm of x square and so on. So then what does this psi does, or the inner product? The inner product of xn comma yn, this converges to x comma y. This is the claim. that we are trying to show. So we will utilize the following fact. We shall use the Cauchy-Schwarz inequality What is the Cauchy-Schwarz inequality? If you have any u and w belonging to V, absolute value of u and w is always less than equal to norm of u times norm of w. So consider the following object. Inner product of xn comma yn, where n belongs to set of natural number, and we have the inner product x and y, which is this limit. Okay, consider the absolute value of xn comma yn minus inner product with x with y. This is the case. Okay, so this is a complex number if it is a complex vector space, and if it is a real vector, this is a real number. So we are looking at these numbers, and if it is real, then absolute value. If it is complex, then it is modulus. So add and subtract the following scalar, which is what? Inner product of xn comma yn minus inner product of xn comma y plus inner product of xn comma y minus inner product of x with y. Let A is equal to inner product of xn comma yn minus inner product of xn with y, and let B is equal to inner product of xn comma y minus inner product of x with y. So what do we have? Norm. So absolute value, if it is real, it is just absolute, or it is modulus A plus B. And using the triangle inequality, mod of A plus B, or absolute value, this is less than equal to mod A plus mod B. So what do we get? Substituting this value back, and A is nothing but A could be rewritten as what? So if you have yn, xn is the first term sen, this is the real number. In this place, if it is come, it's just complex conjugate, and but the complex conjugate is the same. So this is nothing but xn yn minus y, and B, this minus 1 coming in the first place, xn minus x. The absolute value of A plus B less than equal to absolute value of A plus absolute value of B. So what is absolute value of A? This is inner product of xn comma yn minus y plus absolute value of inner product of xn minus x comma y. This absolute value. So what do we get from here? Now if we have two terms over here, inner product, so we can apply in parts. So if you look at this following part, in this part, this would be less than equal to norm of xn times norm of yn minus y plus norm of xn minus x into norm of y. So what happens? Now as n tends to infinity, so xn converges to x, so norm xn, so this converges to norm x, this converges to 0, this converges to xn converges to, this is 0, and this converges to what? This is just y, so this is norm of y multiplied. So this is nothing but this into this, which is 0 plus 0, which is 0. So in other words, this is the absolute value, so this is bounded below. So what do we get? But in fact these terms were nothing but so the absolute value of x and yn minus inner product with x with y. This is what? Bounded by 0. This is always non-negative. In fact, so this is 0. So in other words, as n tends to infinity, so you have as xn, so more proper way would be that xn converges to x, there exists a stage n1 such that for all r greater than equal to n1, norm of xn minus x, or rather xr minus x, this is less than epsilon. So given epsilon, this argument. So similarly, yn converges to y, what does this mean? So given epsilon, greater than 0, there exists a n2, so that for all s greater than equal to n2, norm of y s minus y strictly less than epsilon. So what do we have is that let's n to be the maximum of n1, n2. You take this one, you take n is the maximum of this thing, that works. In other words, as n tends to, if you take this stage, after this stage, if you look at the following sequence, which is what? This is equal, tends to 0 as n tends to infinity. This means what is that if you look at x1 comma y1, next term x3 comma y3, and so on, so on, so on. So this term is that this sequence converges to x comma y as a complex number. Okay. So the map, the inner product, the function on the inner product space, so it's a continuous map. So it's a so even if you have second place as a fixed, so what would be a corollary of this fact is that if you have xn as a sequence which is converging to x, so xn comma y, this sequence will converge to x comma y. Similarly, if you have yn is a sequence converging to y and you have first variable fixed, so x comma yn, this sequence which converges to x comma y. So coordinate functions are also continuous. So inner product, so the map is in fact a continuous operator. So it's a continuous operation, just like the norm is a continuous operation. Xn converges to x, norm of xn converges to norm x. If xn converges to x, yn converges to y. Xn comma yn, the inner product of these, this converges to the limit x comma y. So inner product of the limit is the limit of the inner product.